Hello, this is my submission for homework 5, M5 nonlinear systems. Starting off, question 1 on problem 3. We are asked to find a contour or solve the system up to 4 significant figures doing computations by hand and or using MATLAB. The first step is using contour plots. So here's my code. First, I essentially initialized these equations with the ones presented, except I took, for instance, on this, I took this cosine and subtracted to the other side and set it to 0. So I set all these 3 equations equal to 0. So our f implicit function would work. And I found the f implicit function from not only the solution that was provided by Dr. Nassar, but by also rationalizing that an implicit function is any equation that's set equal to 0 that uses 2 or more variables, as you can see here. So yeah, getting into these initial equations, EQ1 is just equation 1, EQ2 is 2, and EQ3 is 3. You might notice this at x, y, and z. This is here because there are 3 variables, x, y, and z. If you were to add a variable such as q here, be x, y, z, and q. Yeah, this is just here to let the implicit function know the variables. So you can see the first one set equal to 0. That's why this is cosine subtracted. You can see why the x, y, z is subtracted and why all of this here is subtracted. Next to the plot, here's our 3 plots for our 3 equations, 3 different colors, blue, red, and yellow. And here's our limits that help me find the value where all 3 hit. And I'll run that. I'll display that at the end. The plot, which will leave some context out, but I'll try to explain it as best as I can. Question 2 has us use Gauss-Seidel, which is also known as the greedy method. We have an initial guess, and I picked this weird array of numbers here because these 3 values are extremely close to the point that I found from our contour plot. So I'll show that at the end, and you can see that kind of where these values come from. They're really close to that point. We have our loop with I just did 20 iterations, and then here, kind of unlike the first one, solving for 0 by subtracting everything over. We solve for just an x for the first one, a y for the second, and a z for the third. And as you can see, there's still some x's in here, but it's fine because we use these original x's to get us a new x, and then we use this new x like you would on paper to get the new y to kind of override your y, and then you can use your new x and y to override your z and get a new z, and then you just display it here. So I'm going to run it. However, you see that There are a lot of, it looks like it's just diverging. And after the 11th iteration, you get not a number on all three. And I think this is because there are so many values. I lost my spot. I think this is because there are so many values where the three hit that the iterative method can't pinpoint where to go. It just keeps on bouncing around sporadically. Question 3. We use the Jacobian. Similar initials to question 1. Same for loop setup, except now the Jacobian, it's not as fast, but it's more stable. We find all these new values before changing our x's. So we don't use the new x to make a new y. We don't use the new x and y to make a new z. So it's not as fast, but it's more concrete. And after we find all these new values, we replace our old x with x new, old y with y new, and old z with z new. And then we just display it. So I'm going to run that. And as you can see, this method also becomes NaN by the 20th iteration, not a number. However, it makes it up to the 18th iteration with values. So I would say it did its job of being more stable. But as you can see, it just very quickly loses itself and goes to very high values. And I kind of explained why I thought that happened. It also could be my code, but I think it's because there are many values where the 3 hit, so it just can't pick a singular one, even with an extremely close initial guess like this. Question 4 asks us to use Newton's method. So once again, we have our 3 initial guesses, but I put them in a matrix because that's kind of what you see when you do these by hand. So this is pretty much just like your x, y, and z. And you pull these values out. So you pull the x out with big X1, pull the y out big X2, pull the z out big X3. You make your system of equations for computing, similar to how we did in the first method, the Gauss, not the first is contours, but the Gauss-Seidel, or not the Gauss-Seidel, the contours, yeah, that's right, the contours was right. You subtract the cosine over, subtract these, and you subtract all of this. And you make your Jacobian with partial derivatives, so like your first one, you take this first, 1 by 3 array, I think that'd be. Three by 1 array. And then you take a derivative with respect to x, a partial derivative with respect to x, so your 2 stays alive, your y dies, your z dies, and your cosine xyz stays alive. And then you kind of do the same thing with y and with z, and you repeat the process. And then this is your way of solving for Newton's method. After you solve, you update the solution. X new equals big X new equals x big X plus dx. Display it, and then we will replace our, just original array of initial values with the new values. Last question has us use fsolve. So I used this initial SOE, system of equations. Here's you see F that we have here, except I use big X's and really just using the same stuff that you would see, here. It's the same initial guesses on everything. So yeah, you make that. No Jacobian required. And then fsolve here. So we have our big X solution equals fsolve. Inside we have the F. So our system, our initial guess, and optim set. First let me explain tolerance function. This kind of cuts off after 6 significant figures. The optim set kind of like allows you to like modify. It's like a modifier. And then you can display your values here. I don't know that I ran this method. Let me run all these really quick because I'm not sure which ones I've ran. I haven't run. So you can see that's Gauss, NAN. I ran that. Jacobian. This one you can see reaches like a singularity or a bad error. The condition is not a number. And then it just goes to NAN. Then number 5. It tries to get something, but it's kind of whiffing. This value is actually very close, but these two are kind of bad. And as you can see, it says no solution found. Also, I'm going to run this first one because you can't see it. I just want to show you that it runs. The plot's on here. You cannot see the plot. And then next, I'm going to also show like if you delete these, why I think these values are not converging to something. So I'm going to delete these. We're going to run it, and then I'm going to add them back, and then I'm going to cut to the 2 plots. Okay. On to the plots. All right, so here's my first plot. As you can see, this is weird. As you can see, this is the value that I chose. It kind of hits at about here. Wow, that's like perfect almost where I chose. This is kind of an approximation of where the 3 intersect, and I just wanted to show you that. And now I'm going to show you the plots without the limits so you can kind of see where I'm coming from about this not an answer. Here's the plot with no limits, or I guess the boundaries are 5s. And as you can see, there's so many spaces where 3 values collide. It's kind of hard to keep track of. Like here would be an instance where the 3 bodies would collide. And I think the issue with my code is that the numbers just keep on wanting to try and converge to all these different values. Like it would want to converge to this, and then it wanted to converge to this, and then it wanted to converge to, I don't know, something up here, back here. So the The method just couldn't make up its mind, which was, I think, the issue that I was finding. And I just kind of wanted to explain that. Thank you.